And then what would happen is a mic would come to you, you'd be able to ask that question. Please ensure that you state your name and your organization, and then speak into the microphone so that I could hear you, and then I'll respond accordingly. This time is yours. Make the most of it, and I'm hoping that it's going to be a productive session as we go through. Okay, now that I've gone through the housekeeping issues, I'm going to start off by talking about geosynthetics. And our first session is on geosynthetics. The theme of geosynthetics is going to run throughout the workshop today. Let's start by just talking about Macaferry. If you haven't heard of the company, we're going to go through a number of different things in this presentation. Because of time, I'm going to just go straight into it. Now, more than 120 years ago, there was a flood in a city in Italy, and it caused the breaking of the banks along a river. Two brothers who were working with steel at the time, what they decided to do was to take the steel wire that they had at their disposal, weave it into these mesh baskets, and place them with the community that they're working with along the river banks. These brothers were the brothers Macaferry, and the river that they are working on is the River Reno, where we get the name Reno mattress from. Now, this was done more than 120 years ago, and up to today, those gabions are still in place. Now, that's interesting in terms of where it started, but the organization today has spread across the globe with sales in over 130 countries, revenue of 650 million euro per annum, more than 3,000 employees, 20 factories, and 70 subsidiaries around the globe. Now, in Africa, there is a factory in KwaZulu-Natal. It is a 9,000 square meter factory, and this factory produces I'm also going to ask colleagues, please, you keep your microphones muted.
I think, Devon, give us a few minutes. Just like a minute. Tim?
For now, I'd like you to use the chat.
We are good? Technical? Okay.
For those online, if you could type out in the box, in the chat box.
I think, Devon, we can pick up from the question itself. We can continue. Ask the question again for the sake of the participants.
Ronald says reinforcement and soil stability. Excellent. I see that, Ronald.
Devon, can you hear me?
Yes, I can, Jeffrey. If you want me to reshare.
This is karaoke. I want you to pick up from the question itself. We start from the question you're asking.
Yes, so the question is, what are the functions of geotextiles in the knowledge of, from the knowledge of in the house today? So I'm getting responses in the chat, maybe 2 or 3 people online that are in the room, that are not online.
Any guesses?
I'm getting Julia say filtration, separation.
Such a quiet room. Any guesses from the venue? Lost all eye contact. Any guesses? Functions of geotextiles. You use them all the time. Don't feel shy.
Okay, so online, I'm getting a few things, and I can see the people that have attended previously. I'm recognizing the names. I'm seeing Emmanuel say can act as a filter material. Um,
You know it.
Alphonse is saying reinforcement, filtration, separation, cushioning weak soils from settlement, prevents mixing of different soil layers, allows for drainage, improves strength of soil from bed. You got anything in the house, Yugeshni?
No, Devon. So I think our team in the venue
Good.
needs a bit more warming up time.
Karaoke, it's up to you. Hey, maybe you need to get them moving. Okay,
I will.
so colleagues, I'm going to move on. I'm going to move on. I see that many of you like, I'm hoping people in the room have also joined virtually as well. The other, Cleopas is saying geotextile function to provide filtration, drainage, reinforcement, and protection in soil structures. Now, excellent. There's a number of different answers, but it's important to understand the difference between a geotextile and a geosynthetic. Now, one of the biggest challenges that we have is that we've been using the word geotextile and confusing it with geosynthetics. Geotextiles form part of a broader group of material called geosynthetics. And what is a geosynthetic? The word geo talks to earth. So geosynthetic products, it's a polymeric, synthetic or natural material used in contact with soil, rock, and any other geotechnical material in civil engineering applications. Now, on the screen, you can see a number of different products, including geotextiles, geogrids, geonets, geomembranes, geosynthetic clay liners, geofoams, geocells, and geocomposites. A lot of geos that are in there. However, when we talk about all of these products, it's important for us to understand their function. And so what we're going to be looking at today, and it's a key thing that I'm going to show you in the next couple of slides, we talk about the function of geotextiles. And the function of geotextiles may be broken up into, although you see 7, there's actually 8, but I'm going to talk to you about 7 over the next few slides. We have on the screen, you can see separation, reinforcement, filtration, drainage, waterproofing, protection, and erosion control. Many of the things that have been picked up in the chat today when I asked the question. Now let's look at each of these, and it's important that you understand the function. Now, one of the key things, and the reason I'm going about this workshop like this, is for us to understand ultimately, how do designers specify this material in tender documents? Because one of the challenges we have is we say we want a geotextile, but we might mean that we want something else. What happens when we get a substandard material? How do we control that? And so we need to understand the function that is required, and the function would allow us to specify the minimum characteristics that are required in a tender document so that the contractor prices. That when we start looking at filtration, we then start looking at the permeability, and we're looking at the opening size. Now, on the technical data sheet, so if I go back here on this technical data sheet, you'll see that each product that is supplied by any supplier should come with a data sheet with the specified norms in terms of it. Part of that, of course, is the component that we've been seeing in tender documents all the time, which is the mass per square meter. And I hope that this helps you to understand that merely stating the grams per square meter is not enough when doing a talking about textile. There are many in terms of the method of measurement is square meter. It's not roll. It's good meter roll. You want to take all the ambiguity when you're trying to ask for your material. The basis of the payment, what are you including in it? Is it just the supply and not the placement? And so you define that as well. And then in terms of the bill of quantities, how do you specify it in the BOQ? Geotextile for separation, as shown in the drawings, in square meters. And that's generally what we do for specifying geotextile materials. Hope that makes sense. Now, I've gone into a little bit of detail on this one. All other products, I'm not going into this amount of detail, but I'll just highlight the technical requirements for each component. So, a first example for you now to take out your phones. Across the room in the auditorium, as well as those online, I'd like you to scan the QR code. There's a little poll that's up. I'll be seeing the results, and then I'll present it to you shortly. It is 9:03 on my side. I'm going to give you 1 minute to complete this poll, and then we'll share results. So let's have a look at that. Scan the QR code and answer the question. It's multiple choice.
So the code is on the screen. Let's scan and answer the questions kindly.
Thank you very much. I've got 122 people online today, so I should see a fair amount of responses. Are we struggling in the room, colleagues? I'm not seeing any responses at the moment. Got 17 responses already. Okay, I'm just going to give it a few more minutes, another minute. I've got 27, 30. In this workshop, I don't want you to fall asleep. I want you to use your phone. 33 responses. And I am going to stop there and share the responses with you. So in terms of it, I have one of you saying that it's filtration only, drainage, nobody, reinforcement one, 33 or 94% of you that have voted have said it's all of A, B, and C. So the function of geosynthetics, and I apologize, the question on the screen is geotextiles, but it's geosynthetics. Yes, it's all of it, filtration, drainage, and reinforcement. So we can use geosynthetics for all of those particular components. I'm going to move on because of time. Now that we understand the functions of geosynthetics and we understand a little bit about geotextiles, we're going to get into a key area for yourselves, which is pavement reinforcement. And when we start talking about pavement reinforcement, we can talk to separation, we talk to reinforcement, and we talk to drainage. Now, when we're talking about a pavement, there's a number of courses that we're looking at. We've got the wearing course, the binder, the bituminous base, the base, and the sub-base. When we're talking about the wearing course, we talk about treatment, and there's a couple of solutions we could utilize. When we get into the base, this is where we're going to try and distribute that load. And when we're distributing that load, we're going to do that through reinforcement. Where we have a problem with water coming through, we can also start looking at separation and drainage solutions as well, which I'll mention as we go through. So let's start by looking at that wearing cost and what we can do in the wearing cost. Now, when we're looking at the wearing cost, and that wearing cost is meant to distribute that load. The other thing to happen on that wearing cost is we need to make sure that it's sealed, so we get no cracks propagating up into the surface. Now, on the surface layer, it's a regular surface, it's resistant to vehicular loads, and it's got to be waterproof. And when we get into the subsequent layers, we generally on the base, we're starting to look at gravel, and there we're starting to look at the real load distribution. There needs to be good drainage as well in that area so that we take all water that's coming through from the top as well as water coming from the bottom out. Then on the sub-base side, we've got selected material. We're also looking at load distribution. Here more so, it shifts more to water coming from beneath, where we're talking on the sub-base. And of course, in the sub-base, we want to separate it if it's good quality material and the underlying material is poor. We want to look at separation as well. And then potential material. Now, if we start looking at those bound layers, one of the key challenges with the bound layers is the cracking of asphalt layers. And across Africa, and I've worked across Africa now, I can tell you that this is a common space where we put down these beautiful roads. We've got this asphalt pavement, and then after some time, we're starting to get cracks. And cracks can happen for a number of reasons. They happen because of traffic, because of temperature changes, and because of displacement in the road pavement substructure or the structure. Now, when we apply a geosynthetic as we increase the service life of the pavement by preventing fatigue. Concerned about the amount of technical information that I'm going to give you with all of these codes. These presentations are available. There should be QR codes around the room today that say resources. Part of those resources are these presentations. So you can download them. You've got about 2 or 3 days before they expire. Those links expire, but you can download them. I encourage you to do so before you leave the auditorium today. Now, those are the codes that we have. Just moving forward. In terms of asphalt interlayer products, they can be divided into 3 main categories. Now, one of the things that we want to do with the pavement layers is we want to put in geotextiles that can be impregnated with bitumen. Now, when we do that, we allow for an impermeable layer. So as opposed to just putting a seal on the surface, we're now looking at putting in a bituminous barrier that can both provide stress relief and act as a barrier. Then when we start looking at the pavement itself, we can actually improve the modulus of the material by putting in a grid into that material. Now, we've got to understand when we're working with these particular grids, if you're working with asphalt, you're working with high temperature of materials. So our material has to be able to withstand those temperatures. Now, when we look at the grids that are offered by Macaferi, we combine both these functions. We could offer it just as a pavement material, so just a geogrid component, or we can combine both to offer what we call a geocomposite, combining the grid and the geotextile to give us both. If you want to use it, you got it for sealing as well as for reinforcement. Now, in those bound layers, this is where the challenge comes in. So you've got your layer works, but in there, if you've got any cracks, because you're going to have tires moving across the surface all the time, any crack that propagates is going to go into the surface. By introducing a geosynthetic into that layer, what we're doing is we're stopping the crack from propagating onto the surface. Of course, water is one of the biggest threats to pavements. When water gets into those pavement layers, this is where we can get piping of water up through buildup of water pressure, and then we get a degradation of the pavement, which leads to potholes. Now, when we start looking at that material, we have woven geogrids. Importantly, we are talking about grids that are made from glass fibers, which can be used in asphalt layers that are about 35 millimeters. Now, they have a very high stiffness. The characteristics of the material is it's got to be stiff so that when you have deflection of that pavement, it reduces deflection. So it's still flexible, but it's reduced in terms of it. There is enhanced bonding if it is with a geotextile, because it then has that, it is impregnated with the bitumen. The advantage is that it reduces deformation, it reduces asphalt layer thicknesses by 10% and increases the service life by 20 to 30%. An alternative product is also a steel product. So it's where we take our double twist wire mesh and we insert some rods into them. This allows us to have bi-directional strength of material. In the technical data sheet for geotextiles, there was a machine direction and a cross machine direction. So what we're trying to do is to try to make sure that we have strength in two directions. So any particular synthetic material, we need to observe the strength in both directions, in two planes. Okay. Now with road mesh, you can reduce asphalt thickness by 30 to 40%. I have to caution you, in Africa, our asphalt overlays tend to be around about 50 millimeters. If we're going in at that thickness or thinner, then the road mesh does not become effective. So we need to do, because the road mesh needs to at least a 50 plus thickness to be able to add value. This is what road mesh looks like. It's used in asphalt layer works at least 60 millimeters, I beg your pardon. It's got a high stiffness value as well because it's steel. It's three times increase in the pavement life. So that's the value that it adds. There's no weak interface, and because the material is so thin, so the wire strands are thinner, there's good interaction between the asphalt above and below the material. We've got very high resistance to installation damage as well. So a case in point here is a project in the Iraqi border. You can see here, this is a pavement that was initially the initial condition. The solution here in terms of rehabilitation was to mill out 140 millimeters and then resurface with a 12 centimeter thick standard bituminous overlay here. By introducing road mesh, we can reduce that thickness from 120 millimeters down to 70 millimeters. Now, arguably, as I said to you, in South Africa or Africa, our pavement layers are slightly thinner, so the road mesh product, unless you're going with thick asphalt overlays like this, which is not it's not unheard of, because if we look at heavies, lots of trucks coming through, then we can consider thick asphalt overlays like that. This is the milling of the material that you can see, the crack sealing, the road mesh deployment, the road mesh fixing, and then the wearing course that's being applied, and then of course the finished surface thereafter. Another example in an airport runway. In this airport runway, you can see the distressed pavement, lots of cracking, it's very dry. So the solution here was to mill out and place this material. In this instance, they didn't need to put in a sealer, so this product that was utilized was one without the geotextile. You can see the placement of the material. All this work was done at night. So they milled out at night after the plane landed, and all passengers had left the airport. Essentially, it was milled out. Grid was played and the airport was next. So it remained fully open and functional throughout the maintenance period when this was done. Now that's the wearing costs, where we're looking at reinforcing the bound layers. Now we can look at the unbound layers. Now this becomes valuable where we have a shortage of road building material. And this might be the case anywhere in Kenya, where we've got an issue with getting material in from quite a distance that is suitable for our layer work. Now, when you design, it is important to get the right material, but unfortunately, there are times where we can't get that. This is where the cost-benefit analysis must be performed. So whilst I speak about the solutions that are coming in the next few slides, it's important for us to still go back to look at the cost-benefit. Does this actually add value? And you will find that there, in many instances, will add value depending on the distance of material that you have to transport in. This is the typical situation that we have. The roads become so badly rutted that it actually is, you can see key parts that have been formed in the road that we need to drive on. And when we start looking at the principle of rutting, and this is really what we're addressing here, it becomes a bearing capacity failure. So the entire pavement layers can't take that load anymore. You start getting differential settlement. There's some rutting that occurs. There's wet and also contributes to it. There's weak subgrades, and you counter this with thicker layers. And that's really what you do when you're starting to look at this. This is in the absence of putting in a synthetic material. Now, you'll see a number of things coming out there, and because I spoke about functions earlier on, you'll immediately start to realize that there's certain things that we can start adding in here as a synthetic material to prevent these problems. This includes things like, so when we start putting in synthetic material in those unbound layers, we're starting to distribute the load. We're decreasing the load by increasing the area that that load is applied to. So effectively, if you're looking at that load bulb, if it starts here, it's quite narrow. And depending on the quality of the material, that load distribution gets wider if it's stronger. If it's very weak, it will punch straight through here. And that same load gets distributed over a wider area. So that comment about this decreasing the load, it's the decreased net load per square area that's been applied on that material. Now, what we can also do by putting in reinforcement, we make it spreads out further. But what also starts happening is we start looking at separation layers as well to make sure that we don't get the materials mixing. Now, when we apply the design principles for reinforcement in the layer works, there's two key design approaches. The one design approach is we say, okay, so this is our layer that's here. We design it in a traditional approach, and then we introduce grids in there. By introducing the grid, what we do is we reduce the thickness of that material. So that's design approach one, reduce the thickness of material, and we put it in a grid. Design approach two is we keep the thickness the same, but what we do is we increase the pavement life. So you can go, for instance, from 5 years to 10 years or 10 years to 15 years simply by introducing this material into your pavement. Now, the material that is utilized, important that the characteristics come out. In the first one, which is resistance characteristics, that the resistance to biological and degradation requirements. They do have high mechanical performances, up to 100 kilonewtons per meter. I beg your pardon, there's a typo on there, it's kilonewtons per meter. Extruded grid, not WGEG. On this one, it's a high measurement, symmetric and asymmetric tensile. In addition to the machine direction and cross machine direction, in this case, we're saying that if it's a symmetric grid, strength in this direction is the same as the strength in this direction. And you have it's a strength of up to 40 kilonewtons, 30% UTS at 2% strain, and 70% ultimate tensile strength at 5% strain. So what you're starting to see now, when we start looking at grids, you can't just say that the when I tested in a machine is 40 kilonewtons. That's the design strength I'm going to use. I've got to consider how much of movement I'm allowing. If it's moving by only 2%, how much of that strength is going to be done? So this is the character that comes into the utilization of grids in this particular application. So some examples for you showing you unknown layers. You can see here the placement of your grid. When we start talking about reinforcement as a separation geotextiles. Now, essentially, when we're looking at our pavement layer work, so this is our subgrade and we're coming to put in our layer works in there, what will happen is if we're putting in a granular base, and if you have without geotextile on the left-hand side, with geotextile on the right-hand side, on the left-hand side without geotextile, what's going to happen is our material, granular material, is going to be lost into our soft substrate. On the right-hand side with geotextile, whatever granular material that we have is being separated from the two. That you're going to add by putting in a separation geotextile. Function here, separation. Okay, and you can see some examples of different types of geotextiles. These are your woven geotextiles. This is your W2, your C2, and your CW, where you can also you can incorporate it with a grid as well to give you both strength as well as the separation functions. The different types of geotextiles, I'm not going to go into detail, but I did cover it earlier on, your non-woven and your woven geotextiles that may be applied. Now, at the bottom of our layer works, we could have a problem with subsurface water. It's important for us to get rid of that water from our layer works as quickly as possible. Water will follow the path of least resistance. So if we introduce a component within those layer works where that water can go, then we're going to take that water out of those layer works. And what we can do is we can put a horizontal drainage system in called MAC drain. MAC drain is a geocomposite that has a geotextile on one side and a different type of lining system on the other, which can be a geotextile as well, as you can see in this particular application. But there are other examples where you can have it as non-permeable with a drainage core in the middle. Now, what that's doing, and you'll remember when I spoke to you about drainage, drainage is that water that's flowing in this material, not through it, but in it. So water will flow from both directions into this material, and because there's less pressure here, water is going to flow through this material. Okay. Now, in this instance, you can see these clear ridges here. These clear ridges mean that that's going to be the drainage path that our water is going to flow in. So it's important when we place this on site that we know where that's going, because we need to make the water exit from the layer works. Okay, here's a good picture of everything. As you put them together, you can see the macrid AR, which is that glass fiber grid in the bound layers, road mesh in the bound layers. When we get into the unbound layers, we're starting to use macrid for reinforcement, macrid EG or WG. When we get down to the bottom, we want to try and prevent any water from going to our layer works. We can separate, firstly, the good quality material from the poor material, and then we use a drainage component, a drainage geocomposite to take all the water away to the sides of the embankment. Now, designing with geosynthetics, you would typically, you can go through your design codes, but we also have software available that allows you to do that. I was almost inclined to add the software to your resources today. However, these software packages change frequently, and they are updated continuously based on the research and development that we do as an organization. To allow you to access that, we've made most of these software packages available online, so you're always using the latest package. These can be found at www.macaferry.com. You go to our site, you register on the site. Sorry, is that a question? Okay, it's just a comment in between. All right, so from that perspective, you can let's just try and mute everybody. If I can ask you, please, in the room, if we can help me to mute everyone that's not speaking karaoke, unless it's a question. All right. So let's continue. So you can see here that this is the kind of software that we're utilizing to actually design it. A couple of case studies, a few case studies, just in terms of the use of geogrids in your pavement layers. And this is now your typical design, and this is coming out of our design software. So if you design and what comes out of your design is a number of layers. If you take same material, so that is your elastic material, etc., we understand the different qualities of the material. We then introduce a geogrid into it. Now you'll see those two design approaches that we have. The first design approach is keep the layer works the same thickness, and we put the geogrids in. What will happen is the life of the structure changes from 1.5 million passes. It goes to 30 million passes. So you've increased it by about 20 times. The alternative, the second design approach, is then to say, no, we want to keep the design, the life of the pavement the same. All we're going to do is we're going to reduce the amount of material that we utilize. And in that instance, you can see the reduction from 1.13 meters down to 0.86 meters, from 0.7 down to 0.36. Of course, with the bound layers just staying the same. All right. So you can see the change in terms of that reduction of material that's required. Here you see some pictures of a project in Oman with that particular cross-section applied to. That's the application of the extruded grid in the unbound layers, and you'll see a peg that's been put in just to hold that grid in place. That's largely because of when we're placing the material. When you're using a synthetic material like this, it's important to keep it in place for the paving operation so that it doesn't lift up from that bottom surface. Another example here in Africa, this is in the Western Cape, very badly rutted road. You can see the condition of the road. This was after milling. They've got into the unbound layers, put in the macrid EG, and then that is the road on the right-hand side. Of course, we've gone through the, now what are the, how do we, so what I want to highlight for you is I'm not going into the specification, but what I'm going to look at is the key characteristics that we need to specify. So specify a macrid or a woven geotextile or a geogrid is not good enough. We need to make sure that we put in the minimum characteristics. Here, when we talk about the fiber grid, we are looking at the tensile strength, the strain, the Young's modulus, the working temperature. And these are all relevant for those that are working in roads and pavement engineering particularly. This will make sense to you in terms of it. The melting point, we don't want to put this fancy grid in at the minute. We put our we put asphalt down, everything's going to just melt. And so it's important to understand that this MAC grid is for the bound layers. We cannot use MAC grid EG and WG in the bound layers. Okay, so within Macaferi's portfolio of products, I'm giving you guidance on how we select geogrids. The contractor cannot just choose virtually any grid and just want to put it in there. There's very specific characteristics that you need to start looking at. And then, of course, the mesh opening size, which talks to the interaction with the other material. Now, when we start looking at, that is the bound layers. When we start looking at the unbound layers, now we're starting to look at the MAC grid, we're looking at the MAC text, and we're looking at the MAC drain. I'm not looking at all of them. There are a number of different products that you can look at. But if we start looking at the MAC grid, the key characteristics that we're looking at, we want to distribute that load. So it's going to absorb some of this material wants to push away, so it wants to push the soil away. The grid is actually acting as a tensile strength. It's a strengthener. So we need to understand the tensile strength. We can't allow it to move too much before it gets its strength. So the strain becomes important as well. So you can't just merely ask for the tensile strength with strain. Then is the grid going to interact with each other? The junction strength and then the opening size as well for interaction. When we start looking at the MAC text, on the MAC text side, this was for the separation. When we're looking at separation, we need to make sure that it doesn't puncture, material doesn't puncture from one side, from the good quality material into that poor material. So you'll see here puncture resistance becomes important. Puncture resistance is related to the tensile strength of the material. Therefore, you see that there. How much of that product is good, or that material is going to puncture through or move through before the tensile strain is important. The opening size is also important if we're utilizing it for filtration or we're using it for drainage. And then the weight is a component. Now notice, I started by telling you about geotextiles. Historically, we've been asking for geotextiles purely based on weight. Now you see the other technical characteristics that we need to include in the specification when we're talking about that in the tender document. Now we move on to the drainage geocomposite. And if you're looking at the drainage geocomposite, what I pulled out here is something that's called MAC drain one way. Now, when we're talking about one way, we want the water to move in one direction and not in the other direction. Typically, we've got water being pumped up from below. We've got very wet surfaces, or our subgrade is wet. We want the water to come up to our one way, and then it needs to move horizontally and exit our pavement. And so what we're doing is we're using a material like this. You can see it's a one-way geotextile. Its thickness is very, very important in terms of the pressure, because we're going to be putting load on this material. So we need to understand how thick it is. Why is thickness important? That is the capacity of the drainage component. The mass is also important because it just gives us, it's not break. So we got to understand the tensile strength. It's in plane capacity. How much of water can it translate with that thickness? What is its puncture resistance? So in other words, if I'm going to put a load on it, can it just use this material? It's going to break my drainage medium. What's the flux to the normal to the plane? Now, this talks to the permeability of the material. This is where it acts as a filter. Before the water gets into my drainage core, I need to make sure that it keeps the soil back. So this talks about how much of water was allowed to pass through the geotextile. And related to that is the opening side of the geotextile. Now on the other side where it's impermeable, we need to look at how much of water it'll prevent from going through. You can see this composite has a number of different functions. We can't merely specify mass. That's the key thing to take out of all of these things that I'm talking about today. I'm not going to go through that. Let's move on because of time. I'm now going to move on to slightly deeper into your pavement. On the deeper side on your pavement, you now start looking at separation and reinforcement. Now, when we're talking about this, what we're really talking about is, firstly, when we're looking at applications where we're building roads on very soft soil. It is not impossible for us to start putting down piles because we're expecting settlement. But when we are doing this, the spacing of the piles becomes critical. Now, in some instances, we can get away with not putting piles at all. In other instances, we can look at just increasing the space of piles to the extent where we can almost get rid of it in certain applications. Important for us to understand those limitations. Now, when we're talking about embankments on piles, what happens with embankments on piles is that we're actually creating this catenary arch, where ultimately the soil would actually fail or disappear, and then this soil becomes self-sustaining. It'll actually hold that load on its own. Without reinforcement, there is a very specific distance that we can keep this for that arch to form. With reinforcement, we can increase the spacing of those piles, therefore decreasing that cost. Now, when we are designing that, and two methods that we could apply, we could design it as a beam method in terms of that code with multiple layers of low strength geosynthetic reinforcement, equally spaced within granular material fill to average beam across all of these piles. Or we can use the catenary method. The catenary method says that we actually put in a geosynthetic cross, we'd allow that deflection, okay, and then it forms that catenary arch that eventually will be stable. Now, when we're doing that, so we can use a number of different methods, including biaxial geogrids with the polypropylene with a maximum strength of around about 40 kilonewtons per meter, or we can use a uniaxial geogrid, slightly higher strength with strengths of up to 1,500 kilonewtons. So alternatively, you could also use geotextile. There are a number of geotextiles that have good strength. In my experience working in Macquarie in the UK, what we did was we had a primary reinforcement and a secondary reinforcement. The primary reinforcement were strips of geosynthetics that were running perpendicular to each other over the pile caps. In between, so the spaces between if there's a pile cap here, if I'm looking at plan, pile cap, pile cap, pile cap, pile cap, your strips of geosynthetic will run across like this and like this. This section here, which is left empty, becomes your non-woven geotextile as a secondary reinforcement. So there is a method to design around that. In terms of the differences of methods, when you're looking at the installation techniques with regard to the beam method, remembering that the beam method is several strips of geosynthetic. On the catenary method, you'll come and put your first layer of high-strength geogrid. On the left-hand side, you can see the beam method, then you'll come in with selected fill layer. On the catenary method, you're already looking at your second layer of geogrid in the perpendicular direction. If you needed multiple layers, you would continue, and you can see on the left-hand side, as you're going through, you're coming through with multiple layers. On the right-hand side, you've already reached your layer work. You've completed your layer works. So the advantage of a catenary method is certainly a time-saving component that can be applied when going with that high-strength geogrid. Okay. So this just highlights, the next couple of slides just highlights the difference in time and the ease in which you can actually do high-strength geogrids. Macquarie can do both. We do advocate the catenary method, and I'll talk about that a little bit more in the MSEW lecture that I'm going to go into shortly. With the beam method, you need to actually put in overlaps. With the catenary method, there's no overlaps. So there's some other advantages in terms of it. With structural fill, you can actually you have to use well-graded material between the geogrids. With the catenary method, you don't go with structural fill. Everything's above the reinforcement. So a practical example for you, what we're doing in roads is we're not talking about the pavement layers now. Now we're talking about the earthworks. So essentially, when we're getting into the earthworks, the challenge is what you see on the screen right now. We've got soft material on which we are placing our good quality fill material. The problem comes in is that material is so soft that I can get failure right through my good material into that soft material. And so that's what I'm really designing for. Now, importantly, what we are doing is we're not designing for serviceability. We are designing for global stability. A good example to explain this concept to you is a project here in Oman. There was a road that is going to be constructed quite near the waterline. So you can see that the water table is very, very high with some ships in the background there that you can see. And so the solution here to get onto this embankment was to look at stone columns on which they would put in this beam and then come through with the platform above that. As an alternative, McAfee looked at this catenary method, putting in this geogrid, in fact, losing the stone columns altogether, and then coming in with the building of the road. When design and analysis was done, we would typically go through local stability, lateral stability, foundation extrusion, rotational stability. Then we also did a check on excessive settlement, just to understand whether there with regard to settlement. It's there for global stability, although settlement calculations can be done. In this instance, from a global stability point of view, there was no problem with increasing the factors of safety above 1. The problem came in when we started looking at settlement, and on the settlement side, we expected in one particular section that there was going to be settlement of 354 millimeters in a period of time of 175 days. So here, again, I'm going to emphasize, this product was not utilized for settlement. It was used for global stability challenges. And so to circumvent that, what we did was constructed the embankment and allowed it to settle for the 6 months whilst we continued the earthworks across the other sections of the road. After the 6-month period, we had that settlement. Then we came in and did our layer works and continued and completed the road. And so that's how we counted that. It's an important note to understand that all synthetic materials, in fact, all engineering materials have limitations. Just like concrete, we understand the limitations of concrete. We can't put concrete everywhere without some help. Concrete, we've got to put in steel for tension. And that's what we need to understand even with geosynthetic materials. They do have limitations. It's important for you as an engineer to understand those limitations and how to work around that. And the example that I'm showing on the screen is a classic example of how that was done. So that project in pictures, you can see the really poor material. In fact, I hope this was showing clearly on your side. You'll see water pumping up as they put dump rock down, and they were trying to ensure that they got this formation layer in place. All right. Even after we put the material down, you see how nice and how spongy that is. But even after we put that material down, as you see this roller going over that material, you still see a very spongy surface that's there in terms of what has been formed. So that's how poor the underlying material is. Once that was done, and just note that they hadn't put a separation layer. That material can get just mixed into the underlying material. We then place the paneling material down. You can see this is a paneling 400 strength material. It's a molded material. So there's strength in one direction. If you want strength in the other direction, particular to that as well. This is the backfilling and compaction activity, the laying of the road base, and the completed road. In terms of the benefit, it's great talking about these things, but on the cost of the project. The application of stone columns was going to come in at $78 per square meter. Our solution came in at $10 per square meter. So quite a significant saving offered to the client. Again, I'm going to go back to the statement I made earlier. Cost benefit analysis must be done on each and every single project. It's good engineering practice. So I'm not saying to you because I'm talking about geogrids that it's going to solve every problem. We need to be aware of it and how to actually utilize that. Okay. Another example could be seen here is also under building. So this is an extraction, LPG extraction project. They're creating these large storage buildings or structures. And the underlying material was fairly soft. So what they wanted to do was try and make sure that there was no global stability. This was the finished grade, the placement of the paralleling geogrid, and then the cross-laid. And what's important about this is I said to you that it's monodirectional. So here you see the placement in one direction. If you look very carefully, you see the steps in that direction. So it's two directions that material was placed. That's the circular concrete rough foundations completed, and that's the structure coming up. This is the tanks that were constructed and the completed project. Another project that could be utilized, not quite basal reinforcement, but also an application where we're looking at reinforcement, high-profile project. Here we had the problem of actually stabilization against liquefaction. And what was happening here, I'm not sure what's going on. I think some of my images are not coming through. Here we go. So here we've got, they tried to look at 4 separate scenarios because they were increasing the height of this island. They had the possibility of liquefaction and failure of this embankment. And so what they did was they put in layers of paralink. So different options were considered, but instead of going down to the surface, they put the layers of paralink at the top so that we can actually prevent that failure of that embankment. This was a couple of pictures that will just show you what was done. As they're building this embankment, they came in and put the layers of paralink, and that is the completed structure. So just to give you an idea, so whilst we're working on roads, there are other things that interest us as civil engineers that we can actually apply in our day-to-day practice as well. Another project here in Durban, where I'm based in South Africa. Here they were constructing right next to the ocean. They were trying to create a storage facility that would stockpile soya. From that perspective, this was the underlying material, very, very poor material. And from that perspective, I think I'm going to ask you a question here that you're going to put into the chat. Let's see if you can just get your blood flowing before we get towards the end of this presentation. I don't think I've got it. All right, so you can see here, that is the picture that I showed you earlier on, geotextile at the bottom for separation, and then we've come in with the clean river sand above that. Once we've done with that, we come in with the geogrid that's unrolled across the surface. Now, one of the things that we do when we're looking at geosynthetics, we need to make sure that we protect it against damage. And I'll talk about that in the lecture down further down. But you can see here that we place or tip material at the side, and then we try not to ride on the surface. We actually ride on the fill. So we're tipping and pushing away so that we don't ride directly on it and limit the damage to the synthetic material. I love this picture because it shows bidirectional strength of the material. You can see that this is in this direction, that's in that direction. This was then the superstructure coming through with the different components of the application. Okay, so you can see a number of different applications of geogrids applied in embankments and along buildings as well. This was the component I spoke to you about when we're talking about embankments over piles. We can also extend that and integrate that with mechanically stabilized earth walls and structures, which I'll cover in the next lecture. Okay. When we're talking about basal reinforcement, the critical components here are the tensile strength, the aperture size, and the reduction factors. Now, what's important, and I just want to go back there a moment, reduction factors are a key component that must be considered when you're looking at soil reinforcement and basal reinforcement. And I'll cover that as well in the next lecture when I talk about the reduction factors for the materials. I'm going to go through the next couple of sections fairly quickly before I spend a bit of time on drainage and separation. On the coastal side, we start looking at separation, reinforcement, protection, and erosion control. We also look at containment, the component that I spoke to you about earlier on. The challenge here is actually erosion that's caused by wave action, and it does cause it is detrimental to all infrastructure along the coastline. Map tube is a type of product that's ideal for coastal regions because it's UV stabilized and it can utilize the existing beach sand or beach sediment to fill into the particular units. The way in which it works is you pump material into these bags. What happens thereafter is water comes out of the bags and the solids are left into these bags. These are fairly large bags that you can see. And these are utilized, and they put in. There's a number of filling ports that you have. You pump material in. We stitch them as circular units, but then they'll end up in this oblong shape that you see on the screen. That oblong shape is generally has a high durability. It's UV resistant as well. It does protect the coastline, and interestingly, there's different design concepts that we can apply. Very much like retaining structures where we'd have toe protection, we can actually just make sure that it's adequately towed in on both sides so that it can act as a breakwater as well in coastal environments. Design principles, look at some of the principles that you have: sliding, overturning, bearing capacity. It's almost like looking at retaining structures in terms of how they're designed. A great picture here where MacTube has been utilized. You can see along the coastline, some tubes that have been applied, and you can see the protection that we have here, and the buildup of the coastline over time. If you've got roads along the coast which you need to protect, and so this is a possible solution for you along those particular areas. This is some examples in the US and New Jersey, some protection works that have been applied there. You can also put this, the same application can go into, and for those that at some point in time worked in it or may go into it, you can use the MAC tubes for tailings as well. So you can pump tailings into it and then drain those tailings and ultimately take out the dry tailings and then move them into other areas. We also get involved in landfill as well. I don't want to highlight the landfill, rather the application that's going to be highlighted in this section. And here with the landfill, you can see a number of different things that are coming out. Functions of separation, reinforcement, drainage, waterproofing, protection, and erosion control. Now, when we talk about that on a landfill, the key thing here, the currency that you talk to with landfill, whereas roads, when you can talk about kilometers of roads. With landfill, we talk about volume of waste that we can store. So when we're looking at that, there are a number of areas that we can get involved in. We have the bottom lining system. So when we look at the bottom lining system, let me see if I can click on it. Let's just go in here. All right, so we have a top lining system. On a top lining system, we have what we call a multi-composite. We can combine multiple geosynthetics together. This allows for drainage. It also allows for reinforcement on the top of the structure, the capping of this landfill. So there is a product like that. There's also another type of product that's a clay liner. This is an impermeable liner.
Any pressure from you?
Okay, so you have an impermeable liner, geosynthetic clay liner. You also got HDPE liners. This is also preventing, all of these are membranes that prevent water from going into the landfill. And then finally, to protect it from any water that does come through and also any gas that needs to come out, we have a drainage composite like we saw in the roads that's allowing things to go into this core and then exit, not translating into the material below or above it. All right. When we start looking at the bottom of the system, let's see if I can do this. When we start looking at the bottom of the system, here we don't want the leachate or anything to go into the underlying material. So here we've got things like the MAC drain again. We look at MAC Tex for protection. Below the MAC Tex, we have an HDPE liner. So you've got a liner that's here, but I want to ensure that that liner does not have any holes in it. Now, great when I start, but after I start putting the waste in, I could have sharp objects that are going in. How do I protect that lining system? And so I use the geotextile as a protection. So here, the geotextile must be fairly thick for me to be able to protect that material. And then as I go further down, I can use a clay liner as well underneath to prevent any material that comes through from going into the underlying material. Importantly here, I said the currency is actually volume. So when I use traditional materials like clay, and I use particular materials to prevent and limit that from limiting the leachate from going to the underlying material, you can see the volume that it occupies. But on the right-hand side, it's a lot thinner. The system's a lot thinner, so that means I'm increasing the volume, and that's the major currency that we look at when we start talking about landfill. Reinforcing waste, the steepness of the slopes. I'm going through this fairly fast because I'll talk about this in MSEW later on as well. But you can see there's a number of things that you can do here. This is another example of that reinforcement of waste. So you can go steeper and in turn increase the volume of material that you have. I showed you this picture earlier on. So where we got water, contaminated water. Now we need to make sure that that water does not permeate into the surrounding natural groundwater and contaminate it. So here we're putting in a lining system like a HDPE membrane to try and make sure that we cut it off. Finally, as I spoke to you earlier on about this, which is a capping system. The capping system is actually this geogrid. It's a multi-composite. You can see this is a geotextile, and it's a non-woven geotextile. We then have a drainage core. This is to allow water to flow through it. So there's that function of drainage. On the top here, we've got another mat product here. But if you look very carefully, you'll see this continuous strand here. That's a geogrid. So there's a possibility of combining several materials with each other to give you what is called a geocomposite, and that's what this is. Right. Some other examples here in China and Republic. And finally, I'm going to go into drainage. Quick question. What functions do geotextiles play in the base course of a road? And this is just a recap of what it played. And when we looked at the base course, so this was not in the bound layers, it's the unbound layers. The geotextile was utilized for separation, and it could be used for drainage as well. So that's what it was utilized for. Now, when we start talking about drainage, drainage is, we speak about reinforcement. Sorry, where am I? Again, so there's two parts of drainage that we look at. We look at overland drainage, and we look at subsurface drainage. Now, overland drainage is something that you cannot neglect from the roadside. We need to ensure that all stormwater on roads get transversed, so that they translated into some sort of drainage channel. So we need to make sure, for instance, if we've got head walls, we've got to protect that. Groundwater, we've got to try and make sure that we have dissipating structures to take that energy. This lecture is not covering that, and I'll cover that a little bit in the last session that I'm doing today. In this next part, or the next few minutes, I just want to talk about subsurface water. Now, when we're talking about subsurface water, we can get water typically that's flowing beneath the surface. Now, the problem with that is that it leads to several challenges, and this is actually got a lot worse now from that time. You can see here that the problem here is water as well as soil geometry. And what happens when we're talking about subsurface water? It's due to the soil grain size, the structure of the soil, the type of flow of water flowing in that soil, as well as the relative amount of fluid that's present in that matrix. There's a couple of characteristics that go into the look when we look at subsurface flow, including the intrinsic permeability and the hydraulic conductivity. Now, what does a designer have to do when he's looking at water? The challenge with water in there is that it's reducing or eliminating soil cohesion. It does produce horizontal forces if you're looking at retaining structures. It's lubricating your failure plane, and then it promotes uncontrolled movement of your soil particles, which is your piping. And then it can lead to liquefaction during earthquakes, which is then basically translating into movement. The designer has three choices. One is that they can actually, when they're designing, they can either design with that reduced characteristic of the soil, or they're going to look at putting in a drainage medium. And the drainage medium essentially is three-phase design process. One is position it in the right place, make sure that you can allow the water to enter your drain, and then finally you got to remove the water in time. So because of that, what we're doing is, where I showed you this drain previously, when we're talking about drainage blankets, we can then we can replace that drain with just a drainage blanket that allows that water to flow material into a pipe and then exit the system. So it makes it easier to actually handle. We use what is called a drainage composite, which is what I showed you earlier on. Okay, good morning, colleagues. Just for those that are online and not at the venue, I am waiting for confirmation from the venue to proceed with the lecture, the next session. So as soon as I get that confirmation, I will continue. Please bear with us. Yeah. Max, come. Max, come. Come good. Come on, sis. Good boy. Good boy. Sit. Sit. Good boy. Good boy. Good boy.
Check. 1, 2. So for those who are outside, kindly join us. Anybody who is at the lobby, kindly join us. For those who are online, we are back for our second session of the day. I hope you enjoyed the first session. I hope it was interactive enough. And if you have any comment, kindly, as we continue, you can reach out to me so that we can be able to solve any issue. If you feel Divan is too fast, kindly let me know so that we can all be able to understand this. It's a workshop. It's a workshop. I keep losing. You can cut down the music, kindly. So it's a workshop. So you don't have to wait. If you have a very burning question, you can raise up your hand and we can be able to take it as we go by. We want this session to be interactive as you head towards the second session. I hope you've all enjoyed your break and had something to re-energize with. Without saying much, I think we can. Divan, can you hear me?
I can do. Thank you very much. I can hear you. I just said for those that hadn't seen me, I put my camera on so that you can see what I look like.
Oh, there goes Divan. He's not as... there he is. Yeah, we can see you finally. So I think at this point, Divan, you can take over the session and we dive into our second session. Karibu, welcome.
Thank you very much, Karaoke. Just before I get into the second lecture, and I'm grateful for the questions that are coming in. There's some questions that are filtered through on the chat. I've also had some questions come through on my WhatsApp as well. So there are two questions. I know that in between, Yugeshni has responded to some of you, but there are two that I wanted to cover before I get into the next lecture. So Joachim had asked about the design code that is utilized for these kinds of applications, particularly with pavements. The answer that we use, that we're doing with these applications is AASHTO 1993, so it's important that you understand that. Practical examples, there's a wealth of practical examples that come into our case study component. Drop me a message and then I will actually try and send that through to you as well. Unfortunately, I wasn't able to put the case studies into the your access to information and what's the next steps from here after sitting at this workshop. So let's start talking about soil reinforcement fundamentals. And I heard Yugeshni say earlier today that it's quite cold in Kenya. But I'm going to tell you where I'm from. Let's start by saying that to you. I'm from the sunny province of KwaZulu-Natal, and I live in a city called Durban, which is famous for its beaches. As you can see, it's winter here in Durban, and it's in the upper 20s here in Durban. Pleasant weather. I know that we've been in the press recently for all the wrong reasons, but we are generally a friendly lot of people in South Africa. We like to be friends, and I think that's great. When I grew up as a child, I would often go to the beach, favorite thing to do, and we enjoy the beaches in Durban. But more importantly, as a child, I would go in and I find myself sitting on the beach as a child, and now my children do it as well. Well, they've grown past it, but when they were kids, they used to do this. They put some sand into a bucket and then turn this bucket over. So if the sand was a little bit moist, it would form a sandcastle. Yeah, so what you're seeing on the screen now is a sandcastle. So I'm gonna just pick your brain a bit. So just get a bit of interaction and see how things go in the next couple of minutes. I want us to test our imagination a little bit, right? So if we take this bucket, the sand that you see on the screen, a sand castle that you see on the screen, you put a little bit of pressure on that screen, so on that bucket of sand, or that sand without the bucket now, put some pressure on the top of that sand. Now you're going to go to the chat very quickly. I'm not looking for hundreds of responses, just one or two. what's going to happen when we actually put some pressure on that sandcastle? So wherever you are, just type out in the chat group. That's what I'm just looking for 1 or 2 answers so that I can get some interaction from the group. So what happens when I put some pressure on that sandcastle? On the top, so where you see the flag on the top, I'm going to put some pressure right about here. Maybe take my hand and press it on the top. What's going to happen to that sandcastle? Somebody, that's right, engineer Ekakoro, you've said that it will collapse. Correct, it's going to collapse. Now, if we put some pressure on it, any kind of pressure, it's going to collapse. Now, let's try and use our imaginations wherever we are. As we're filling up this bucket with sand, what we're going to do is, you get even a sheet of cardboard. We're going to take a cardboard, and around about there, as we're filling up, we're going to put a cardboard there, then we're going to put another cardboard there. Now, again, I'm going to ask the question. You're going to go to your chat again, right? When I do that, do I need to apply more force or less force to cause it to collapse? Or will it collapse at all? Your thoughts? I've got 168 people that are online. I should get at least 2 or 3 responses. Talk to me today. Help me make this interactive. I'll wait. What's your thoughts? More, Lawrence, great. You're going to put more force. All right. So that's principally what's going to happen. So if I took cardboard, which is a fairly soft material in context, and I put it in as layers in this material and put some pressure, all of a sudden it's going to take more force. Now let's extend this a little bit. Wherever you're standing, right? Wherever you're sitting today around Kenya, you could be joining online from another country. Let's make this bucket that we're using from a sand castle bucket. Let's make that bucket a little bit bigger. All right. So we take maybe a dish, a larger dish, and we're going to put multiple layers of plastic. All right. So multiple layers of plastic in that bucket. Or I like what we started with the karaoke saying, you can use his shirts to do it. So we'll take his shirt and throw it in there, cut it up. And sorry, we're going to cut it up today, right? But we're going to cut it up and put it into that bucket and then fill it up again. Now, the question is, would you have the confidence to stand on that bucket of sand? I'm looking for some responses. For those that are online, you got an opportunity to speak to me. What's going to happen? Confidence that it will collapse, not collapse. Just 1 or 2 responses I'm looking for, not everyone. Who's brave enough today? Karaoke, I don't know if you can volunteer a response from the room, from the house today.
Anybody?
Blair, right, Bernard? Not collapse, not collapse. Okay, so we seem more confident. I don't know if it's because we're using Karaoke's shirts. You think his shirt is a good quality because he said he's going to contribute today. But the thing is, what you're starting to understand is that the soil does not have any tensile resistance. But by introducing some sort of barrier in there, some sort of material in there, we're becoming more and more confident with the fact that by just putting that in, it can possibly withstand a force. Okay. Now, I want you to think about things a little bit further. Now, even though I had that cardboard or Karaoke shirts, as he indicated, that was in these layers here. What happens if I take my hand and I rub it around the edges? Now, what's going to happen is that surface is going to erode. Okay, so when we look at soil reinforcement, specifically with retaining walls, we have what we call a facing here, and we have a reinforcement, 2 different concepts, okay, or components. And we must have a connection between them. And that's what makes the system, okay? Now let's extend that analogy a little bit and show you some experiments that were done. And maybe I see universities that are here, professors that are here today. Maybe you can try this in your universities and promote engineering and geotechnical engineering at universities. So here there's a university in Italy. They created this little box that was here, as you can see. What they've done with that box is they've had a facing here, which was made out of timber. And what they then did was they looked at creating cardboard facing. So they had a facing, you can see here a facing, and they're creating reinforcement with cardboard. As I said, cardboard, they used cardboard, all right? Then they created these strips. You can see these strips that are here. Those are the strips. There's your cardboard. So there's a positive connection between their reinforcement and their facing. Then they've come in, they've put it into that box, all right? They've kept that facing in there. So they've kept that timber facing in there, but they start filling up this box now with sand. As they continue, you can see they're compacting as well. So that's the similar action to what we would do typically on the ground. And then we've reached the place where we fill it up completely, remove that timber facing on the front, and check to see whether this layer or this component can hold a bucket of sand. Now, let's go back to what we said earlier on. We said, would you be confident if you stand on that mound of sand that it will take your weight? Possibly not collapse. And you can see what's happened just by using cardboard. We've actually enhanced the strength of that mass of soil. All right? That is the principle of soil reinforcement, colleagues. Like you have steel that reinforces concrete, like I mentioned in the last lecture, we have material like this, which is your synthetic material, geosynthetics, that reinforces soil. Importantly, what we need to understand is we need to understand the characteristics of the soil. We need to understand the characteristics of the reinforcement. Now, if I said to you, if it was cardboard versus suddenly when I said Karaoke's shirt, everyone felt a bit more confident. That material seems stronger than cardboard, right? So we've got to understand the material characteristics. Okay, that is the reinforcement. We've got to understand its interaction with the soil. We've got to understand the facing, and we've got to understand the connection between the two. All right? Now, what principally are the design principles we're looking at when we talk about walls? And there's a number of different design codes that we can talk to. The design codes, you can see there's AASHTO, there's the Federal Highways Association, WAGEC 00011, PS 8006, SANS 207, and Eurocode 7. So those are the codes that you can utilize when looking at mechanically stabilized earth walls. MSEW, MSE, mechanically stabilized earth, MSCW is mechanically stabilized earth walls. The two codes that I'm going to be referring to today in this presentation is BS 8006 and SANS 207. You are welcome to use any of the others, but just for the purposes of setting a platform, creating some ideas to how to understand these concepts, I'm going to be talking to those two, BS 8006 and SANS 207. Now, SANS 207 talks to, and it has this specific thing that's here, right? A number of diagrams here. And you can see it talks to retaining walls and embankments, soil nails, fill slopes, basal reinforcement, etc. I'll go through all of those in the next slide. So here we talk about slopes. And when we're talking about, we talk about walls and slopes, we're talking about retaining structures. And what's common here, as you can see, a reinforcement and a facing. Reinforcement and a facing. So you have walls and you have slopes. Very quickly, for those that didn't see the whole of that slide, in your chat, very quickly, for those that did not attend the lecture, the first lecture that I did a couple of months ago, I want those others to answer. What is the key difference between a wall and a slope? You're going to respond in the chat. I want to see what your responses are. What's your take on what's the difference between a wall and a slope? We're going to type out in the chat. How would you classify a structure a wall? And how would you classify a structure a slope? I'm going to go again to Karaoke. Can we see if we can get at least one response today from the room? I'd welcome you to even walk around and just ask somebody randomly.
Yes, I can see a few engineers whom I know by name.
Oh, great. Thank you.
I can see Engineer Kidagisa, saidia hapa kidogo tafadhali. Thank you, Engineer.
And they walk to the front.
So Engineer Kidagisa is giving a response on that.
Yes.
Personally, I think a wall is vertical, 90 degrees, and a slope will be an angle, not 90 degrees.
Okay, great. Thank you very much. I see that mic moving around. Great.
One more
Somebody
response.
else?
One more, kindly. Engineer Match? Let's get one more response from Engineer Match.
Yeah, good. I think a wall is a retaining structure,
Yes.
but the slopes are not retaining.
Nice. Good thought process. So what it leads us to believe, and I'm going to put my microphone on because I like to have the discussion with you, and I'm able to see. I'm actually appreciating the camera that's in the venue as well, so I can actually see you. Is what I'm appreciating is there's varying responses. We're saying that it's 90 degrees. The first response was 90 degrees. Now we're saying it's retaining. The other one's not retaining. And so what BS 8006 and SANS 207 starts to do is it starts talking to an angle. All right, so it says a specific angle that you're talking about is 70 degrees, not 90 degrees. Anything steeper than 70 degrees is regarded as a wall. 70 degrees and lower is regarded as a slope. Now, this is important in terms of, if you look at block walls, if many segmental block walls in industry, I think in Kenya as well, there might be there might be a number of block walls that are coming into the market. Most of these structures are sitting at around about 65 degrees. This means that they're sitting as slopes and not as walls. So let's move on now with the presentation as we go through. So the answer is 70 degrees, and Alphonse, I think Owayo, you did get it right at 70 degrees. I hope that's your knowledge, and not that you read the slide very, very quickly, because I had that on the slide previously. So when we start, so there's walls and slopes, 70 degrees is the magic number. When we start looking now at other components, we talk about basal reinforcement, and I did cover this in the last lecture. We're looking at basal reinforcement on soft foundations, basal reinforcement on piled embankments, and we also have basal reinforcement spanning voids. Now, the situation of voids is when you start having sinkholes. In Gauteng, in South Africa, there's a prolific problem there where we've got voids that occur all the time. Construct these roads, and all of a sudden we've got this massive sinkholes that occur. And I understand you could have some problems in Kenya as well, where you've got this. And this is where you can put in a geosynthetic across those voids, or where you potentially see voids, to prevent these kinds of problems from occurring in the future. The last area that we talk about reinforcement is interface shear layers. Now, when you're looking at putting a thick layer of soil on a surface that is inclined like you see on the screen, this is where we now start putting reinforcement in. You'll remember at the end of the last lecture, I started speaking to you about clay,
Morning.
Let me mute everyone. Okay, so in the last lecture, I spoke about the top lining system and the bottom lining system. So on the top lining system, where we're putting topsoil over the entire landfill, this is the classic example where we need to reinforce that soil. And so this is the other application when we look at SANS 207. Now, let's start with the different components, but there's a few technical things that we must talk about. So when we're talking about soil reinforcement, we're also looking at the service life of the material. Importantly, on a structural point of view, if we're looking at temporary works, we're talking about 1 to 2 years. Short-term works, we're looking at 5 to 10 years. Industrial usage is now sitting at 10 to 50 years. If we're looking at long-term, and on the road side, we're generally sitting at something between 60 and 120 years. This is your highway embankments, we're sitting at 60 years. Retaining walls need to be there for a longer time, 70 years. Long-term, we're looking at highway retaining walls and highway structures. Your bridges, bridge abutments, 120 years is your design. Now, this is important because we need to understand what's happening with that reinforcement. How long does it need to last? And how is it going to perform with time? What you're seeing on the screen right now is the force that's applied to this reinforcement. So essentially, we're going to be subjecting this reinforcement to a tensile load. Now, when we start looking at reinforced soil walls and slopes, we find that as we're constructing, the load is going to increase. We go higher and higher and higher. There's more load applied to it. Then once we've reached that point, it's fairly consistent thereafter. The load is not going to decrease thereafter, all right? Of course, we've taken in and we've factored in our live loads, and those live loads come into it, unless there's a significant volume increase, but largely, I mean, you're going to take a truck out and start putting a plane on the road, that's when you're going to increase the load. But other than that, in terms of it, the load is fairly consistent for what we've designed it for, okay? When we start looking at embankments on soft soil, so initially when we're building the embankment, it'll load and load and load. Then eventually what happens is if it's in soft soils, there will be some settlement and the soil starts acting on its own. So it starts protecting itself, but the load will be applied, but that load will then decrease as that slight failure mechanism occurs. So there's some settlement, and then it actually reduces, the soil starts acting on its own. When we start looking at piled embankments, you load it, then you get that arch that occurs, and then you get a slight decrease, but the material does start taking load first before that load decreases and the soil particles lock in with each other and produce that arch. If you're looking at basal reinforcement over voids, there's no load initially because it's supported with soil. There's no void there. The minute the void forms, you're going to get this load that's being formed or applied, and then thereafter it starts settling with regard to, if you've got no maintenance, it'll absorb it. Otherwise, if you start filling that void up, then that load will decrease as well. So it's important that we understand how the loads are applied across on these reinforcements. Now, when we're designing, I specified in the last lecture that we are generally designing for ultimate limit state and not serviceability limit state. We need to understand that. When we're looking at ultimate limit state, we're talking about total collapse of the structure. Destabilizing forces are higher than the stabilizing forces. The safety margins are determined by the application of load and the material factors. There is an exaggeration of the destabilizing forces. So we're factoring up the forces, and what we do is we reduce the stabilizing forces by applying the reduction factors to each of the components related to the materials that are resisting that. Some pictures of ultimate limit state. This is what we're talking about, absolute failure. So visibility limit state is where we start saying it's not going to collapse, but we start looking at cracks, we start looking at some movement, no collapse altogether, but we're still going to have some movement down the line. Now, the key differences, as I said to you, is 70 degrees, and correctly pointed out by someone in the chat, and as I've spoken to you about earlier on as well. 70 degrees, that magic number. Now, when we start looking at the design of walls and slopes, it's important that we understand this concept of walls and slopes. When we're putting loads on, what are those loads? The loads that we apply is essentially, if we look at the static load is the earth pressure. So this is the earth pressure. This is your triangle that you get. With depth, you have your higher pressure, your surcharge, which is your load that's coming in, your external load that's coming in, and then you got your water pressure that's coming through from that perspective. Now, what that will do is those are the forces acting on the wall. We will test the wall for bearing capacity. We'll do things like overturning. What does it do in terms of overturning? We look at sliding. We look at global stability. Now, when we're looking at walls and slopes for reinforced soils, we look at exactly the same thing. So we'll still look at sliding. We'll still look at bearing capacity. We'll still look at global stability as well. So the entire slope. Now, the change here, when we're looking at reinforced soils, is we start looking at internal stability. And when we're talking about internal stability, we now start talking about the reinforcement. The reinforcement will break at this failure zone. So the theory here is saying that this entire mass of material, here, is going to, in this application, in this example, this one and this one, all of these are going to be they're acting as one block. In this one here, when we look at internal, this line that we show here is the failure surface. We assume that everything in front is going to be mobilized, And if we get a failure surface here, it means that each one of these reinforcements is going to break. So it's going to break in tension. Or if we're getting closer to the top here, we'll find that it'll pull out with this block of mass, this massive block here is going to actually start moving or mobilizing. All right, so it's either pull out or rupture. Okay. Now, a useful rule to understand is it's a rule that applies not just to reinforcement, but it also applies to mass gravity gable walls as well. The useful rule to apply is that that base width we start with is 2/3 the height. So whatever that height is, this width here is 2/3 h. Now, when we're doing the checks, we will do internal stability checks. We will check the maximum tensile stress that that reinforcement will take. We will look at the reinforcement pullout to see how much of force to pull the reinforcement out of the soil. And we'll look at the facing connection test. So remember I said to you there's reinforcement, there's facing, and connection between the two. How much of force is applied at that connection point? There's different methods that we can apply to look at the internal stability check methods. Checks, this is your tie-back wedge method and your coherent gravity method in terms of how we do that. Now, the design process, so your inputs, your analysis, and what your outputs are, we generally input the geometry of the whatever we're going to design. We look at cross sections, we look at long sections, we look at any constraints such as, for instance, culverts, you've got barriers, etc., the road surface. This becomes your constraints in terms of what you need to do. The other input parameters that we need when we're looking at reinforced soils is soil characteristics. What are the soils underneath? What soils are we going to use to put in for the structural fill, the material that's sandwiching the reinforcement? Where's the water? How far up or behind the wall is the water? What's the loading? And depending on where you are in the continent, we'll look at the seismicity as well, because that's also a load that will apply to the structure. When we perform the analysis, we do a sliding check of the entire block, an overturning of the entire block. We look at the bearing capacity. We look at the global stability. Internally, we'll start looking at rupture. We start looking at pullout, and we start looking at connection, as I've indicated in the last slide. Now, what do we get out of the process? What we start getting out is the type of facing that we select, and I'll show you different types of facings later on in the presentation. Then we'll start looking at the reinforcement itself. What we are talking about when we're looking at the reinforcement is what type of reinforcement are we looking at? What length is the reinforcement? And what's the spacing of the reinforcement? And then from that, we will develop the detailed specification, as I've spoken to you in the first lecture today with the geotextiles and the other materials. Now, what we will do is we will look at the different components, as I've said to you earlier on. You can see some design principles of embankments. Just 1 second. I hope I haven't missed a few slides here. But yeah, this is some of the things that we will start looking at in terms of the design principles for these particular components. Now let's start talking about the reinforcement that goes into the embankment. Okay, so any of these embankments in the different applications. Now I said to you, we're going to subject this material to a tensile force. This material has the ability to resist that force. So I'll go into a lab and I will test this material. I said in our design process, what we do is we factor up the loads, but we reduce the strength of the material to look at the ultimate limit state design. How do we reduce those factors? Now, this is not a straightforward process. It is a process that involves several considerations when we look at designs. Now, let's take a step back. This structure that you're seeing on the screen is 24 meters high, okay? Being 24 meters high, would we allow that kind of structure to utilize paper or card as the material for reinforcement? And the answer simply is no, we don't do that. As engineers, we wouldn't do that. But why wouldn't we do that? That's the important question. That why could be related to the strength. We're not confident about the strength, yes, but what about the durability? What about the consistency of that cardboard? We could be very careful as to how we put the cardboard down to make sure it doesn't tear. how does it interact with the material on the ground after we've installed it? What about if it's a natural material, cardboard? What about insects? Me a product that I could utilize as it was a plastic gabion that could be utilized in Africa. Question to them was, what standards are you testing this to? Lo and behold, they said, no, we do lots of standards here in China. But I wanted to know what was the international standards that were utilized. And so, colleagues, these are some of the things we need to start asking of our suppliers. What tests are you using to actually test your data? Local ones, great, but we need those that subscribe to international standards. And this creates uniformity and a degree of accountability with regard to those standards. Now, when we test, now I mentioned to you the design lives. They're going through from 1 to 2 years all the way to 120 years. Does it mean that we check the performance over 120 years? Does it mean that all goods that were not in existence for 120 years can't be sold in the markets? And the answer is simply no, we don't do that. What we do is we test what we predict what's going to happen in the years ahead. Now that extrapolation process
require a lot of technical expertise to solve very complex solutions. We are soon going to witness the implementation of the bridge across the Likoni Channel. It's a very complex project. And I want to urge all of us to pay a lot of attention because they have been done elsewhere, but we are picking the technology as we move along. And some of the discussions that we are having today are very relevant. So I want to urge everybody to pay very keen attention.
Oh, so
that, of course, the size is linked to the size of the mesh. So it makes sense that there is something that covers that area. The geotextile that is utilized behind the gabions, and by now you should know what a geotextile is. You either have a woven or a non-woven, and I'm hoping that you remember that when we're using gabions, we're largely using a non-woven needle-punched geotextile. We also mentioned the construction tolerances of the walls or structures that we're constructing. So as opposed to the wire or the mesh, we now start talking about if your wall is supposed to be 3 meters high, it's not 4 meters high. So we're making sure that the construction tolerances are within particular limits. It does include something on project site preparation, and then it also talks about gabions sizes and size references. So showing you some of the tables that are there, you'll see that this is the first deviation that we see. The nominal size of the mesh here is 50 millimeters for a mattress that's up to 0.17, whereas in 1580, it spoke to 60 millimeters as that size. That dimension there is the dimension between the twists, as you can see in the picture. And here, this is the size of stone that you could utilize for gabions. So ideally, you want a mix of stone. You can't have it too small because it can come out through the gabion. You can't have it too large because you don't get the right density of the gabion. And that as well is something that must be controlled when doing gabions. This is the table that talks to the degree of accuracy or the tolerances that you're allowed to construct. And then when you're talking about specifying gabions in SANS 1200 DK, you can see that it says separate items scheduled for gabions of galvanized wire, for gabions of PVC. 23. The connections really articulate. So there's no need to change that really. The ability requirement was brought into question because when we're designing as engineers, we've got to understand the design life that's associated with whatever we're designing with. So whether we're looking at a glass grid reinforced pavement, a reinforced wall, whether we're looking at a bridge, we need to understand what that design life needs to be. So the shortcomings was across the board. There was no linkage to time. The other key thing that happens is that we started speaking about corrosion which is a chemical process. What happens if we take wire and we put it into a wet environment where water flows? So besides corrosion, for engineering purposes, let's go back to where we started this today. I said we are all engineers, and as engineers, all right? So in terms of that, the key differences was the fact that we started talking about engineering purposes. Wire specifications were more or less the same. Wire coatings changed quite considerably from SAN 675% of aluminium with that coating. We had PVC, but there's also PA6 that's now been included. So there's a lot more that's been included in terms of the number of products. And then the environmental level and design life, this also changed. It went from nothing in 1580 and 675 to a detailed description in table A1. If you were making notes wherever you are today, whether virtually or in the venue today, take that note down, table A1 in EN 10223, because that is a key design table that you can utilize to select your wire. Then in terms of the product definitions, it was only gabions and mattresses. Here we started saying that there's some specification when using it in wet applications, it must be metallic coated with the plastic coating. Aging and corrosion was included, and mesh type was generic. Now we're starting to talk about some other components that talk to the durability and longevity of the wire. So where SANS 1580 was only talking to boxes, so they some sort of rectangular or shape. It had some shape, right? It's a box particularly. When we start talking to 23.3, we start talking about variants of products, so a variety of products, including TerraMesh, gabions, etc. All right, so it's enhanced that. So where 20. Anything in excess of 25 years that's coming through, and depending on the design life, you then choose that. So how you utilize this table is you start with your design life. So you'll say, what is my design life? You'll also look at your conditions that you want to go through. So you'll define it in terms of the conditions that are here, and then you'll select those conditions. I start with wet conditions, and in the temperate zone, so you start in this zone here, this part of the table, and they'll ask you whether you want to go up to 120 years or in excess of 120 years. And then based on that, you can select, if you're sitting in this zone here, you can choose a product that's PVC or polyamide with the zinc aluminium coating. All right. As much as it says that, Macaferi is currently doing a product called Polymac. And Polymac, does it now mean that we can't market it in terms of this particular table? And the answer is simply no. What happens here when I say no, I mean there is an allowance for it in 23.3. It says more advanced organic coatings with an equivalent or superior corrosion protection may be considered in order to improve the assumed working life. So in this instance, what we do is we come in and we've got to prove that the coating that we have is actually better than other products. All right. I did mention earlier on about the welded product and the importance of making sure that we distinguish between a welded product and a double twist structural element. Now, just going back to the Polymac, what we have done as a company is that we've done some extensive testing on the Polymac against our PVC product. In addition to doing the normal testing of salt spray, Macaferi has undertaken an exercise where we've put our wire in a wet abrasion test. So we've taken it through like a washing machine, continually exposing it to wire. And at the end of this lecture, I'll try and show that to you. I've just taken it out because of time. But what it has done is after we go through a wet abrasion test, we then expose it to salt spray to understand how it performs under abrasive and corrosive conditions. Interestingly, Polymac does perform a lot better than your PVC products. And I'll try and show you those slides at the end of this presentation. Now, importantly, when we get to gabions, now because of that, we've got different types of coatings. We need to understand how to specify gabions. You no longer can just say gabions 3. That's not the way it works. And so there's a lot of color on the screen right now, but this is now telling you how to specify a gabion. So in your bill of quantity, you'd write something in line with gabion in accordance with, we're writing in South Africa SANS 23.3. If you want to go to a European standard, you write EN 10223. Gabion, that's the size of the unit. Sorry, that's the type of unit. 2 by 1 by 1 is the size of the unit. This is your mesh type 8 by 10. Okay, I spoke to you about that earlier. The wire diameter is 2.7 millimeters. Zinc, aluminium, that's the metallic coating. Polymac, this is your plastic coating that you put in. So all of those things need to go onto the specification when specifying gabions. This may be said for gabions. This is the different wire diameters that you have. It could be said as well for Teramesh units, Reno mattresses. And when I talk about Reno mattresses, it's important for me to also explain to you the changes in technology with Reno mattresses. Material flowing down. So when I say flowing,